this video, we're going to continue our discussion of rates of change, and we're going to segue from this sense of an average rate of change to what we would refer to as instantaneous change. So in other words, change at a single point rather than change over an interval. So before we talk about that, we need to discuss tangent lines. We looked at secant lines with respect to average change. The idea of a tangent line is going to relate to this idea of instantaneous change. So while a secant line cuts a curve, in other words, it passes through the curve into locations, a tangent line just touches, it only touches the curve. So in other words, you can think of it as passing through the curve at a single point. It doesn't pass through 2 points, it passes at a single point and it lays against the curve at that single point. Now while a secant line represents average change, the average rate of change between those two y values, those two function values, as we transition from one x value to another, a tangent line represents instantaneous change. It represents instantaneous change at that single point. So in other words, if we were to zoom in infinitely close, look at that single point, just as you enter that point and just as you exit and move to another point, if you were to look at the change at that single point at an infinitely small level, that's the idea of what the tangent line represents. It represents instantaneous change at that single point on the curve, not between 2 points, but just at that one point. Now the tangent line at any particular point on our graph must be parallel to the curve, which is why it only touches in that one location. So a tangent line can look a variety of different ways depending on what point we are tangent to. Now I want to emphasize that it has to be parallel to the curve at that point. So when we refer to a tangent line versus a secant line saying that the tangent line just touches the curve, what we're focused on is that one particular point where it is touching. We have to keep in mind that when we draw that line, it may touch the curve at other locations, but what we're focused on is what the tangent line looks like in relation to the one point in question, the one point that it's actually intersecting at that we care about. So for instance, this particular point right here, the tangent line at that particular point would be a line that just passes through that point. But notice if we were to draw a line like this, and I'll just draw a little line segment, if you were to continue that line, it would eventually cut through the curve in another location. That's okay. What we're focused on is what the line looks like at the particular point in question. And in this case, it just passes through that point and it lays parallel to the curve at that location. Now, a location like this, for instance, the tangent line again is going to be parallel to the curve, and it's just going to pass through that single point. So it would look something like this. We might have another point. Let's look at the ones that are at those little valleys. This would also be a location where we might have a tangent line like that. Again, notice if we continued that line, it would pass through the curve at other locations. But again, the idea is what's happening at that single point, it's just passing through the curve at that one point at that particular location. Here we have another one where it looks like the tangent line might be horizontal, something like that. And other locations where we might have something diagonal, so maybe something like that. So the tangent line can look a variety of ways just depending on what location we're talking about on the curve. So what we want to investigate now is how we would actually determine what this tangent line looks like. So number one, what would the slope of the tangent line be? And then number two, if we know the slope, well, can we find the actual equation of that tangent line? So if we're looking at a function, looking at a specific point on that function, number one, what is the slope of the tangent line at that particular point on that particular graph? And then number two, if we know the slope of that line, what would the actual equation of that specific tangent line be? So we're going to take this idea of average change and we're going to take it one step further in order to develop this idea of instantaneous change. So we're going to use some of the things we've used before and we're going to add in some other things as well. So the idea of the secant line, we're going to revisit that, and then we're also going to revisit limits that we've talked about before. So we can generate the tangent line from the secant line, specifically by drawing the secant line that passes through our point that we're going to call P. And keep in mind, again, when we did a secant line, so for instance, if we wanted to draw a secant line between these 2 points, it would be the line that passes through both of those. You have to have 2 points in order to draw a secant line. But say we're focused on this point specifically, and this is just an extra point that we have in order to draw the secant line. But suppose this is the point where we want to also be able to find a tangent line that just passes through that particular point on that curve. So the idea is if we start with a secant line that passes through our particular point in question, and then take that neighboring point, the additional point that we drew the line through, we want to move it so that it approaches P. And we'll draw a picture of this in just a moment. We want to move it so that it approaches P. Okay, so say we have something like this. Again, say this is our point in question. This is the neighboring point we use to draw the secant line. The idea is that we want to take this particular point and move it along the curve so that it gets closer and closer and closer to our actual point. In other words, so we're moving not only the point, but we're also moving the secant line that we would generate through the point in question and that neighboring point that we use to draw the secant line. So let's look at a picture of this and explain a little bit more detail based on the picture we had before. So this was the diagram we saw before. We used this to talk about average rate of change, and we also used it to verify this difference quotient formula, which is just another way of expressing this idea of average rate of change. So suppose this is the point in question at which we want to draw our tangent line. So what would the tangent line look like right here? Well, it's got to lay parallel to the curve and only pass through the curve at that one point. So our tangent line would look something like that. Okay, now what's the problem with trying to find the slope of that line? Because let's say the goal is to find the slope of that tangent line. If we're talking about a secant line, we can easily find the slope of a secant line because we have, number one, 2 x values, and then number 2, 2 y values. So y2 minus y1 over x2 minus x1, that represents slope. We can also do it in function notation, and then based on the x and x plus h notation, the slope is also represented by the difference quotient. Okay, so what's the problem here? Why can't we just use that strategy here? Well, the problem with trying to find the slope of this tangent line is in order to find slope, automatically you need 2 points on the line. You have to be able to determine how the y values are changing in relation to change in your x values. Well, the problem at this location is if we're talking about this particular line, we only have 1 point on the line. Because it only passes through this function's curve at one location, we don't have any information about any of the other points on the line. They could be anything. We don't know exactly what they are to begin with. So because we only have 1 point on the line represented, we don't actually have enough information as it stands to find the slope of that line. We would need an additional point to find the slope of that line. So the idea is we're going to use this secant line, and we're going to make some gradual changes to this secant line in order to generate the tangent line. So what would that look like? Well, the idea is we're going to take this extra point, the extra point on the secant line, not the one we're focusing on, but the other point that we use to generate that secant line to find the line slope, and we're going to gradually move that point along the curve so that it comes closer and closer and closer to the actual point at which we're finding the value of the tangent's slope. So what would that look like? Well, we're taking our original point, which is of course a good ways away from the point in question, and we're going to move it a little bit at a time. Okay, and as we move that, we're moving the secant line as well. So just to do it in pencil, so I don't make this diagram too crazy, if we were to move that point to that new location, well, this would be the new secant line right there, something like that. That would be the new secant line. Okay, So what's changed? Well, what's changed in addition to the secant line is the coordinates of that additional point. Again, not the point that we're focusing on, but the additional point that we use to draw this line and find its slope. So this new point, as we've translated this point along the curve, would be somewhere like this in terms of its distance from the original point. And of course, it would have a new y value going with it as well. So what's changed? Well, what's really changed here is h. Remember, h was defined as the distance between our actual point, our actual x value in question, and the additional x value we needed in order to have two associated y values as well. So we've shrunk the value of h. It's now a smaller amount. Now we can keep doing this. So say I maybe move it over here. So that would be my new point. Again, the idea is I could draw a secant line right there as well. So that would be the new secant line at that new location. But because the point is even closer to the original x value, now h has shrunk again. So we're shrinking h each time, and we're pulling this additional x value so that it's closer and closer and closer to the original x value, the one where we want to calculate that tangent's slope. The idea is as we keep doing this, so suppose we have a point here that's very, very close overall to the original x value. Well, again, we now have a new associated x value, which means the value of h is also even smaller. At that particular location, this would be our secant line, something like that. So what's happening over time as we continue to move this point closer and closer and closer to the actual point we're focusing on is what we're doing is we're taking the secant line and we're using the secant line to essentially approximate what the tangent line looks like. So every time we move that extra point closer and closer to our point of focus, we're getting closer and closer and closer to the shape of the actual tangent line. So if we were to take the point even closer, say it was right next to our original point, maybe something like that, really, really, really close. So our new x value would be here. Our new h value, again, would be really small because the 2 points are a very small distance away from one another. We would draw the secant line through there, and the secant line would almost look exactly like the tangent line. But the benefit of having these 2 points rather than just the 1 point is having the 2 points, that gives us enough information to be able to calculate a slope. Because if the idea is we want to calculate the slope of the line we're generating, again, we need 2 points to be able to do this. But the closer and closer and closer this point gets to the point where we're drawing our tangent, the closer and closer and closer the secant line gets to essentially being the same thing as the tangent line. So if we allow this point to move in such a way that it becomes infinitely close to the actual point in question, then for all intents and purposes, we have generated the tangent line. And if we can then, of course, calculate the slope of the secant line, well, the secant line and the tangent line look basically the same because those 2 points are infinitely close together. Well, this idea of moving closer and closer and closer to a particular value, that's kind of the idea behind a limit. When we talked about limits, that's kind of the idea there. So we're taking a particular value and we're allowing it to approach another value. So we're allowing this point to approach the other point. But what we're doing there in terms of actually affecting x or another variable is we're actually affecting this variable h. As we move this extra point along the curve, we're taking our original x value and we're shrinking the distance between that x value and then the x value in question. So what's really changing is this value h, this value that represents the distance between our point and then the extra point we're using to generate our line. Now, because we're allowing h to get closer and closer and closer to where we originally started, essentially what's happening is we're allowing h to approach 0. If we're taking this extra point and moving it closer and closer and closer to the point in question, then what we're doing is we're shrinking the distance between the 2 points. We're allowing the distance to go to 0 so that our 2 points are infinitely close together and our secant line and our tangent line look basically the same? Well, we decided that the difference quotient was the formula that we were going to use to calculate the slope of our secant line, regardless of what that secant line looks like. So if the idea is we have a secant line right here, where our 2 points are infinitely close together, then the secant line's slope expression, this difference quotient, that's going to represent the slope of the secant line. But if we take this slope but allow h to approach 0, in other words, again, shrink the distance between the 2 points in question, then that is going to generate the slope of our tangent line. So again, take the slope of the secant line, but allow the h value to get smaller and smaller and smaller and smaller until the 2 points are infinitely close together. And that's going to represent our instantaneous rate of change. If the idea is that these 2 points are infinitely close together, then it's instantaneous change to go from one to the other. Because they're so close together, you're not really moving to go from one to the other. If you were to zoom way in on this particular location and look at what's really happening. If we allow h to go to 0, then essentially we're just looking at what happens at that single point at an infinitely small location. So rather than taking average change, our instantaneous change is going to be closely related to this. It's going to be the slope of our secant line, which again we're using to approximate our tangent line. So same expression, the slope of our secant line. But as we allow that point to move closer and closer, again, the idea is that we're shrinking the distance between the 2 points. We're allowing that distance to go to 0. So if we take this particular expression and then take the limit of that expression as the value of h approaches 0, that expression is going to represent the instantaneous rate of change. In other words, the rate of change at that infinitely small location, or alternatively, it's going to represent the slope of that tangent line at that one particular point. This expression is going to be very important in calculus. So having our difference quotient, but not only the difference quotient, which represents average change, but then taking the difference quotient and allowing the value of h to go to 0, to go to where it's infinitely small. That is going to generate the slope of our tangent line, what we think of as instantaneous change, the rate of change at that single point on our function's graph. So again, just to reiterate what we essentially just demonstrated there, the slope of the tangent line will follow the slope of the secant line. They'll basically be the same thing. Although, again, keep in mind the secant line passes through 2 points, the tangent line only passes through 1. But the slope of the tangent line and the slope of the secant line will be the same thing overall if we allow our value of h, the distance between the 2 points on the secant line, to approach 0. If we allow our value of h to approach 0. Another way of saying this is that the slope of the tangent line at our point, which has a coordinate x and then a y coordinate f of x, is the following expression. It is going to be the limit as h approaches 0. So again, we're shrinking the distance between the 2 points. We're taking that to where the distance is essentially 0. It is going to be the limit of that expression representing the slope of the secant line. That is going to be the slope of our tangent line. And again, why did we have to come about this at such a sort of alternative point of view? Why did we have to come at this very indirectly? Well, the reason we had to come at this kind of concept indirectly is because, again, in order to calculate a slope, you need 2 points. But if we're talking about a tangent line, we only have 1 point. We can't calculate slope of a line just having 1 point on that line. So the idea is if we take another point that's really, really close to that particular point, that is an infinitely small distance away, allowing that distance, that value of h, to approach 0, then we get so close to the actual tangent line that for all intents and purposes, the secant line and the tangent line look the same, just because the 2 points are so close together. So that's the general idea for calculating the slope. And that expression has a specific name. That expression, the slope of the tangent line, in other words, taking the difference quotient, but allowing h in the difference quotient to approach 0. This expression is what we call the derivative of our function. It is the derivative of our function f at whatever x value we're looking at. So think of x as the location where we draw our tangent line. F is the curve, the function represented here. X is going to be that particular x value on that curve. The derivative here is going to be the slope of the tangent line at that particular location on our function. So formally defined, for a function f of x, y is equal to f of x, the derivative of this function at a particular x value is going to be this function. Notice it's an f of x, but we have another notation there. That's called a prime. So we read this as f prime. That's going to be one of our notations for describing the derivative, f prime. That is going to be the function defined as f prime of x is equal to that limit of the difference quotient. So the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, why are we thinking of this as a function? Well, if we allow x to just be a variable, we don't choose a specific x value, then just as finding the difference quotient found us a formula for calculating the average rate of change, taking the limit of the difference quotient will then give us a formula for calculating the slope of the tangent line at any particular x value along the curve. Now this is, of course, provided that this limit exists. There may be certain locations on our function where we can't actually evaluate that limit, where that limit doesn't actually exist. And in that case, we have a different issue. In that case, we can't actually find this expression, what we're calling the derivative of our function. But if we can in fact take this limit, we can evaluate the difference quotient and then take the limit of that expression as h goes to 0, then what we say is that f is differentiable. It is differentiable at that particular value of x. So there are different versions of this word derivative. So the word derivative is a noun. That's going to be the noun. Differentiable is the adjective version of the word derivative. And if we're talking about the procedure used to find the derivative, a couple different ways to say that. We can say we find the derivative, we evaluate the derivative, we differentiate. That's going to be the actual verbal form of derivative. Take the derivative is the same thing as differentiating a function. So every time we find this derivative, we draw the tangent line at a single point, this particular line representing instantaneous change at that single point on the curve. We always follow the same sequence of operations in order to find this particular value, regardless of what our function is. So the first thing we want to do is we want to write the difference quotient. Find and fully simplify the difference quotient for our function. So remember, that is the expression f of x plus h minus f of x divided by h. And as we determined, again, that is the slope of the secant line between 2 points across an interval, which represents the average rate of change of our function across that interval. So again, we need to simplify that, focusing on what we focused on in the last video, talking about evaluating the difference quotient. From a simplification standpoint, the goal is to try to cancel the h in the denominator. And there's a very specific reason for wanting to do that. The reason we want to do that is because we then want to find the limit of that expression as h approaches 0. So why does canceling the h in the denominator have something to do with evaluating that limit? Well, here's the limit we're evaluating. Here's the difference quotient. We're evaluating the limit as h approaches 0. The easiest way to evaluate a limit is typically going to be algebraically. In other words, we typically just want to plug in the value of our whatever variable we're allowing to approach a specific value for. So here we want to evaluate where h, not x, we notice we have a couple variables here, specifically the variable h, we want to evaluate with h at 0. Well, based on this expression we have right here, directly plugging in h equals 0 would result in division by 0, which we know is undefined, which would then lead us to this idea that maybe the limit can't be evaluated, maybe the limit doesn't exist. If we can take the difference quotient and first simplify it and somehow get rid of that h in the denominator, then we'll find another version of this expression where we can just substitute in that value h equals 0 and we can evaluate the limit that way. So now let's look at a few examples. So again, keep in mind there's all different ways of expressing what we're trying to do. If we're asked to find the derivative, that means take the difference quotient and then take its limit as h goes to 0. We can be asked to find the instantaneous rate of change at a particular x value. That means the same thing, same directions. We could also be asked to find the slope of the tangent line at a particular location on our function's graph. Also the same thing. So those are all different ways of saying we're finding this value that we call the derivative. So let's try an example. So we want to, for this function, f of x is equal to 3x plus 4, so a linear function, pretty simple function. Number one, we want to find the derivative, f prime of x. That means take this function, find the derivative, and then we also want to evaluate the derivative, specifically with an x value of 2. And we'll explain in a minute what this really represents, what that really means. Okay, so finding the derivative, finding this expression, break it down into steps. Number one, we want to find the value of the difference quotient, fully simplified version of the difference quotient for this function. So our difference quotient is defined as f of x plus h minus f of x divided by h. Okay, and we're evaluating this expression for this function specifically. So f of x plus h says take the rules for f and replace our variable with the specific input x plus h. So as we substitute, that's going to be 3 times, not x, but x plus h plus 4. So that is going to be f of x plus h minus f of x, no changes to it, so minus 3x plus 4, all divided by h. Okay, so let's keep going. Here in this first set of brackets, we need to distribute the 3. So that's going to be 3x plus 3h plus 4. And then our second set of brackets is subtracted, which means we can also distribute that subtraction and remove the brackets. So minus 3x minus 4, all of that divided by h. Okay. Now the focus again is on simplifying to the point where we can get rid of the h in the denominator. The goal is to eliminate this h. So let's see what happens in the numerator. Well, we have a bunch of things that cancel. We have a positive 3x and a negative 3x. So those are equal and opposite. They reduce to 0. Positive 4 and a negative 4, also an equal and opposite. So what we're left with in our numerator is then going to be 3h, and then we have that h in the denominator. So we're now left with an expression where we have a common factor of h in our numerator and denominator, which means that it is then going to cancel out, and so that simplifies down to 3. So that is going to be the fully simplified version of our difference quotient for this particular function. Now if we want to take the derivative, the goal is to find the derivative of this particular function. We then take our difference quotient, whatever it happens to be, in this case it happens to be just a 3, and we want to evaluate the limit of that expression as h goes to 0. So f prime of x, our derivative of this function, is defined as the limit as the variable h approaches 0 of the difference quotient, which in this case is just 3. Now this is kind of a strange limit to evaluate, because normally if we're evaluating algebraically, the idea is that we typically want to just be able to plug in whatever value we're looking at for whatever variable we're using to approach. Here we would plug in for h, but notice the expression for our difference quotient doesn't actually have an h. There isn't actually anywhere to plug in h equals 0. So if that's the case, then that means we don't really have to do anything here. We don't have a variable to allow to approach 0. The actual difference quotient is just a constant value, which means if we take the limit and there's nowhere to plug in anything approaching 0, well, the value is just going to be 3. So we don't actually have to do anything there. There's nothing special that happens if we're just taking a limit for some variable and it's just a constant function. The variable isn't actually present in that expression. So what does this represent? This represents the slope of the tangent line. This is the value that represents the slope of the tangent line for any x in our function f of x. That's what that represents. So for any x value, if we look at the point associated with that x value in our function f of x, that is going to be the slope of the tangent line at that particular location. And what's strange here, what normally doesn't happen, is there isn't actually a formula here. It's really just a specific constant value, which means that's going to be the slope at all locations. So f prime of 2, what does that mean? Well, it means we're taking the function defined as f prime of x and evaluating it with an input of 2. So we're taking this function and evaluating it with an input of 2. Well, notice there's no x here. There's nowhere to substitute a value of 2. This is just a constant function 3. So f prime of 2 is just going to be 3. There's nowhere to actually plug in a 2 and evaluate with that specific input. So when we say f prime of 2 is equal to 3, what we're saying here is that the slope of the tangent line, we're saying that the slope of the tangent line at x equals 2, at that specific x value in our function, we're saying the slope of the tangent line at that location is 3. It's going to be 3. And this is not surprising, because if you think about what this really looks like, this is a linear function. So if we're talking about a linear function, we're talking about something where there's not really a curve, there's not really anything changing. So if you were to pick any point along that particular function's graph and take the slope of the tangent line at that point, well, visually speaking, the tangent line and the actual graph of the function are going to coincide with one another. If we want the graph we draw to be parallel to that particular graph but pass through the point in question, well, the only way that can happen is if the tangent line and then the graph of the function itself, they actually are the same graph, just one laying on top of the other. So that means the slope of the tangent line at any location, and also specifically at the location where x equals 2, that slope is going to be 3. Now that is specific to a linear function. Because we're talking about a linear function, we're talking about drawing a line that's tangent to another line, automatically that just means they're going to be the same line. And that again is specific to the fact that this was a linear function. As the functions become more complicated, this will not necessarily be the case. So when we take the derivative, we're not going to find just a constant value. And so when we find the slope at a particular location, evaluate the derivative for a specific x value, we will find that the values change as we apply it to different x values. So let's try another example. So for f of x is equal to x squared, we want to find the derivative. And then we want to find the derivative at x equals -1, so f prime of -1, and also an equation of the tangent line to the curve, to the actual graph, at that same location at x equals -1. So we want to start with the derivative, which means then we're also starting with the difference quotient for this function. So difference quotient, simplify it, then take the limit as h approaches 0. So for this particular function, our difference quotient, f of x plus h minus f of x divided by h. We're going to evaluate this expression for this particular function. And this was actually a function that we calculated the difference quotient for in a previous video. So I'm not going to do the extra work there. Revisit the notes from the last video. The expression for the difference quotient for this function is going to be 2x plus h. Okay, so again, we calculated and simplified this difference quotient before. That's going to be the difference quotient value for this particular function. So if we then want the derivative, we're taking the difference quotient and we're going to take the limit of that expression as h approaches 0. So we're taking the limit as h approaches 0 of 2x plus h. Now you need to be careful here because notice we're taking the limit as h approaches 0, but we actually have two variables involved here. We have both the variable x, our independent variable, and then the variable h, which we use to think of as distance when we're talking about drawing that secant line. That's the distance between the 2 points on the secant line. Since our limit is with respect to h, we leave x alone. We're not doing anything to x here. All we're doing is allowing h to approach 0. And because we can directly substitute in a 0 here without violating any algebraic rules, without dividing by 0, taking the square root of a negative number, we can substitute 0 in here and we don't run into any issues. That will be the easiest way to evaluate that limit. So evaluated algebraically, this limit will be 2x plus, substitute 0 in place of this variable, so plus 0, which is equal to just 2x. So what this represents is the slope of the tangent line to this particular function's graph for any x value. It's a formula for finding the slope of the tangent line for any particular x value. So if we want f prime of -1, what we're asking for then is if we go to the location on this graph where x is -1, what's the slope of the specific tangent line at that particular location? And so we take our function defined as f prime of x and we evaluate it with a specific input of -1. So that's going to be 2 times -1, which is -2. So -2 is the slope of the tangent line at x equals -1 if we're looking at the graph of f of x equals x squared. And just as a matter of just showing you what this looks like in general, why this actually makes sense, say this is the xy coordinate plane, x squared is going to look something like that. It's our parabola centered at the origin, both tails pointing upward. Well, let's say this is the point where we're at x equals -1. So this will be x equals -1, which means the associated y value would be +1. What we're doing here is we're drawing the tangent line at that particular location on the graph. So that's our tangent line. The derivative at x equals -1 is the slope of that line. So we're saying that the slope of that line is -2. And just based on looking at the picture, that makes sense. It is a downward sloped line, so the slope is going to be negative, and it's not one unit rise over run, so rise 1, run 1. We have to rise more and then run less in order to go from point to point along this line. So that slope makes sense, and that in general is what it represents. So it's the slope of that tangent line at the location where x equals -1 on the graph of this function. So now we want to take that one step further, and we want to find an equation of the tangent line right there at that particular location. So in other words, what is the equation of that line? That's the question we want to answer. Okay. Now when we say equation, typically we want something in slope-intercept form. So y equals mx plus b. That's going to be the goal, to find something that looks like that. Now in order to find an equation of a line, we need typically two things. So we're going to use what we call the point slope formula. This is going to be the formula we typically use to generate a line. So it's going to be y minus y1 is equal to m times the quantity x minus x1. This is not a final form in most cases for finding the equation of a line. Think of it more as a formula used to generate an equation. So based on the name, we need a point to use this formula, and we also need a slope. Well, this is going to be the slope. That's going to be the slope we use. It's the slope of the line in question. So what we also then need is going to be a point. So if this is our slope, we need a point. In other words, what's the point on the actual graph at that location, the point where we're drawing our tangent line? So we need that to evaluate our difference quotient. Now here's, or not the difference quotient, excuse me, the equation of the tangent line. Here's where you're going to have to be careful, because notice we now have two functions. We have the derivative, which is its own function, and then we also have the original function itself. If we're finding an actual point on the graph, we're focused on the function itself. This function, the derivative, is a function for finding slope. That's going to be the formula to find the slope at any single location on this graph. If we want to find an actual point on this graph, we have to use the actual function itself in order to find that. So specifically, we want this point. We want the point in question where we drew our tangent line. So we know that x is going to be -1, because that's the location we're talking about. X is -1. That's where we evaluated our derivative. So that means f of -1 is going to give us the associated y value. So that's going to be -1 squared, which is 1. So that means our point has the coordinates -1, 1. So we have our slope, we have a point, and so once we have those two components, we have enough information to use point-slope form. So keep in mind the two variables that don't have subscripts, those are our dependent and independent variables. Everything else we're going to substitute with an actual value. So m is the traditional variable used to represent slope, and then x1 and y1, those are going to be the coordinates of this point. So using our point-slope form, we have y minus y1, which is 1, so y minus 1, is equal to m, which is -2, times x minus x1, which is going to be -1. So watch your signs here. We have subtraction as part of our point-slope formula, but we're subtracting a negative number. So let's clean that up. That double negative turns into an addition. Okay, we want to distribute our -2. So y minus 1 is equal to -2x minus 2. And then because point-slope form is preferable, it's typically an easy form to graph. The only thing we need to do to take this equation and put it in point-slope form is to isolate our y. So if we add 1, move that over, we're going to get y is equal to -2x, and then -2 plus 1 will give us -1. So this is going to be our tangent line. That is the equation of the tangent line at x equals -1. That is the actual equation of that line we have drawn above. So just to give you a sense of all the layers here, the slope of this line, that's what came from the derivative. We couldn't immediately find the slope. We can draw the line. We know what the picture of the tangent line looks like, but we can't immediately find its slope because it only passes through one point, and we know we need 2 points to find slope. To find the slope of the tangent line, that's when we use the derivative. That, by definition, is the slope of the tangent line. So take the average rate of change, the difference quotient, and then allow h to approach 0, which means you're then taking the 2 points using average rate of change, allowing the points to grow closer together, infinitely close together, and then that's going to be, that limit is going to give you the expression for your slope. We evaluated this function at an x value of -1, which gave us a slope of -2. That is the slope of that tangent line. That is the instantaneous rate of change for our function at specifically x is equal to -1. And then using the point-slope formula, this is now the slope of the line we want. All we need then is an additional point, but specifically here we want the point in question, the point at that particular x value. So we know the x value is -1. To find the associated y value, we use the function itself, not the derivative, but the actual function representing the graph here. So that gave us a point, and then evaluate it, simplify it to whatever form you want. That is going to be the equation of our tangent line. So let's look at another example similar to that, different function, but same kind of direction, same idea for what we want to accomplish. So for f of x is equal to 1 over x, so we have a rational function. We want to find first f prime of x, so find our derivative. Then we want to find f prime of 2, the derivative when x is 2, and an equation of the tangent line to the curve at x equals 2. So those two parts will go together. And then also we want to find the value of our derivative at a different x value when x is 0. So let's start with the derivative first. And I'm going to write it here above. We shouldn't need too much space. So our difference quotient, always start there. So we have f of x plus h minus f of x over h. Specifically for this function, and this was another function that we evaluated the difference quotient for in the previous video. So again, go back and revisit that. If you want, you might consider pausing the video and just making sure you can evaluate the difference quotient again. Make sure you can evaluate it and simplify it down. And when we simplified this one, we ended up with negative 1 over x times x plus h. That was the simplified version of our difference quotient. So notice it has nh in the denominator, but the original h that came from the difference quotient expression is not there. This h is a different h than this one. So in finding the derivative, we want to take this expression and evaluate the limit of that expression as h approaches 0. So f prime of x is defined as the limit as h approaches 0 of this expression, negative 1 over x times x plus h. Now, as before, be careful because now we have two variables involved. We're only taking the limit with respect to h, so x is independent of that. We leave that x alone. All we have to worry about is the h. So here we want to allow h to approach 0. If we can evaluate this algebraically, we want to. So we're going to sub in 0. Now, immediately that might seem like a problem. We're putting 0 in the denominator. But putting 0 in the denominator here does not result in the whole denominator being 0. If we put 0 here, notice we still have other things in the denominator. So subbing in a 0 there is not going to be a problem. It's not going to make our denominator 0. All that it's going to do is make that h go away. So we end up with negative 1 over x times x plus 0. So x plus 0 is just x, and then x times x is going to be x squared. So our derivative is negative 1 over x squared. So that is going to be the formula we use to calculate the slope of the tangent line at any x value on this curve. Okay, so specifically now we want to use this formula and find f prime of 2. So f prime of 2 says we're taking our derivative, this formula for the tangent line slope, and we want to know what is this value when x is equal to 2. So that's going to be negative 1 over 2 squared, which simplifies to negative 1/4. So negative 1/4 is going to be the slope of the tangent line at the point when x equals 2 on our function's graph. So in other words, if we were to graph this function, look at the point where x is 2, this is going to be the slope of the tangent line at that particular location. So now we want the actual equation of the tangent line. Well, this is going to be our slope. This is the slope of the tangent line. Now we're going to use our point slope formula again. So we need to know what the point is going to be that we use. I'm going to go ahead and write the formula for point slope over here. This will be the formula we use to find the equation of our line. It's going to be y minus y1 is equal to m times x minus x1. So we know what m is. Now we need to know what x1 and y1 are. Well, because we're looking specifically at the location where x is 2, that's going to be the x value we want. But the question is, if this is the x value we're looking at on this function's graph, what y value goes with it? So that's going to be the question we then need to answer. So if x is 2, we want f of 2, which is going to be 1 over 2, which is 1/2. So that means the ordered pair is going to be 2, 1/2. So this is going to be the point we use. That's the location where you can imagine drawing the tangent line. We drew the tangent line at that location. This is that line's slope. We want to know what is the actual equation of that line at that particular location. So let's sub in what we have. So y minus y1, our y value, which is 1/2, is equal to our slope, which is m, negative 1/4, times x minus x1, which is going to be x minus 2. And now it's just a matter of simplifying all of this down. Now we do have some fractions here. Don't be alarmed. We'll deal with them as we need to. So we want to start on the right-hand side, distribute that negative 1/4. So distribute it to the x. That's just going to be negative 1/4 x. And then negative 1/4 times negative 2. Well, first off, two negatives multiplied together make a positive. And then if you need, think of this like a 2 over 1. So that means the numerator is going to be 2. The denominator is going to be 4. Well, 2 over 4, we know that reduces to 1/2. Okay, now we need to isolate our y, add this 1/2, move it over. So that's not going to affect negative 1/4 x, that term is finished. Okay, but we're taking an existing 1/2 and then we're adding another 1/2. So 1/2 plus 1/2 is going to give us positive 1. So that is going to be the equation of our tangent line. So if we were to draw the tangent line to the graph of this function, specifically at the location where x is 2, this would be the equation of that line. And keep in mind, this is a unique equation. We draw a tangent line, it is unique, so the equation for it is also unique as well. Now we were also asked to find f prime of 0. Well, we already have the formula for the derivative, so now we're just subbing in an x value of 0. So f prime of 0 is going to take our formula for the derivative, and we're going to sub in 0 in place of x. So that's going to simplify to negative 1 over 0, which is undefined. We've run into an issue. That can happen. What that means is that at that particular location, our derivative is undefined. So we would say, based on this, at x equals 0, f prime of x does not exist. And another way of saying that, based on using the adjective representing having a derivative versus not having a derivative, if we can find a derivative, we say the function is differentiable. So for instance, at x equals 2, we were able to evaluate the derivative expression with no problems. So we would say that this function is differentiable at x equals 2. Because when we evaluate the derivative expression for 0, we run into something that's undefined, we could also say, in addition to f prime of x does not exist here, we could also say f of x is not differentiable at that location. That is another way of saying the same thing. And that'll be the preferable way of saying it. We want to use these particular terms appropriately. This is going to be a good time to use it. So at x equals 0, f prime of x does not exist. Another way of saying this is f of x is not differentiable at x equals 0. So at that location, what that means is that we cannot actually draw a tangent line. Anywhere on your graph where you can draw a unique tangent line, the function is differentiable. If it's a location where you cannot draw a unique tangent line, or maybe you run into a slightly different kind of issue, you find a particular location on your function's graph where the function is not differentiable. So let's formalize that a little bit more, because we can formalize the idea of when a function is and is not differentiable. Are you just going to have to guess? Are you just going to run into issues? You can actually determine ahead of time where your function is and is not going to be differentiable. So again, remember, ultimately the derivative represents the slope of the tangent line at a particular location on our function's graph. So a function will not be differentiable. In other words, the derivative is undefined under any of the following conditions. So 3 different situations we run into where we can't actually evaluate the derivative. The tangent line doesn't actually work the way it needs to. So number 1, you cannot differentiate at a discontinuity. Anywhere where there's a discontinuity in the graph, you cannot differentiate. So that can look a couple different ways. Why is there not a derivative? Well, there's no point to touch. You can't draw a tangent line where there's a hole, where there's a break in the graph. And again, that can look a couple different ways. So one example is, suppose you have maybe a curve, something like that, and then a hole, and maybe the actual point for the graph is somewhere other than along the actual curve we're drawing. Well, we could draw a line through this particular point that passes through this point and this point only. Number 1, though, that line is not going to be unique. We can draw any line we want that only passes through that point. But in addition to only passing through that point, our tangent line has to lay parallel to the curve. Well, in order to lay parallel to the curve, we have to draw it in relation to the curve. But it won't intersect that point if that point is not along the curve. So anytime we have a discontinuity and there's no point to touch, that particular location represents a point where we are not differentiable for our function. Now keep in mind the other locations along this function, so for instance right here, pretty much anywhere else, we could draw a unique tangent line, and that would represent a location where the function is differentiable. So we're focused on specific x values at which our function is not differentiable, not blanket statement the function is not differentiable, but it's not differentiable at these specific locations. Now another location where our function is not differentiable is a corner, and that's not really a technical term, but you kind of know what that means. So suppose, for instance, we have a graph that looks like that, something like that. This particular point represents a location where our function is not differentiable. The reason it's not differentiable here is because there is not a unique tangent line. So we could have a tangent line that looks like that lays parallel to that side of the curve, or we could have a tangent line that looks like that lays parallel to that side of the curve. So which one is it that we want? Well, ultimately the answer is we can't definitively say which one we want. The tangent line is not unique at a location like that. So anywhere where we have a sharp corner where it's not smooth on the graph, that also represents a location where our function is not differentiable. And then the third location where we potentially have something that is not differentiable is any location where we have a point with a vertical tangent line. That's because at a location where the tangent would be vertical, the slope at that location is undefined. A vertical line has an undefined slope. Well, if the derivative represents slope, at that point the slope is undefined, so we can't actually evaluate the derivative. So suppose we had a function that looks maybe something like that. At that one location where the tangent line would be vertical, that would be a location where our function is not differentiable. If we could draw a line that's vertical, the slope of a vertical line is undefined. The derivative represents slope, so at that location the derivative, the slope, is undefined. Any other location, as long as there's no discontinuity, there's no sharp corner, there's no vertical tangent line, then we can say the function is differentiable. We can find the derivative, we can draw the unique tangent line at that location. So let's look at a graph, and let's categorize each of the highlighted points as either being a location where our function is differentiable or where the function is not differentiable. So we have points A through J. We want to categorize all of these particular points. So the first point here at A, that would be the actual point. It is continuous. There's no discontinuity. There's no sharp corners right there. And the tangent line would definitely be a diagonal line. It would not be a vertical line. So that represents a location where we are differentiable. Now at B, notice there's a hole in the graph. That hole represents a discontinuity. So automatically, if there's a discontinuity, we can't differentiate at that location. So we are not differentiable at B. Now C is similar. There's a discontinuity, but we have an actual point. It's just been translated below that curve. But still, there is a discontinuity. The point is not along that curve, connecting it at that location, making it continuous at that location. So also, at point C, we are not differentiable. Now point D would be right here. It's continuous there. There's no vertical tangent line, but there's a corner. So are we going to lay tangent to this side of the curve, or are we going to lay tangent to this side of the curve? Ultimately, we can't answer that question. So that also represents a location where our function is not differentiable. Now at point E, at that location, we are differentiable. It is continuous right there. There's no sharp corners. And our tangent line would be a diagonal line. So we are differentiable right there at point E. Now at point F, notice we separate from one branch of the graph to another. That is the location for a discontinuity. So we have a point on one end, and then the curve continues at a different location, picks back up. But again, it's a discontinuity. So are we drawing the tangent line here? Are we drawing the tangent line here? The answer is we're not doing either. There is a discontinuity. Our function is not differentiable there. Okay, at G, it's continuous at that location. We don't have a vertical tangent line. It's not a sharp corner. It's a nice smooth curve right there. So it is differentiable at G. At H, continuous at that location. No vertical tangent line, no sharp corners. So we're differentiable there. At I, now I is kind of unique. I is not really a sharp corner like this one is, but notice that we stop and then suddenly we curve. It's a straight line. The graph is straight and then it suddenly curves. So it does represent a corner. Are we going to be tangent to that side? Or are we going to be tangent to that side? Neither. It's not differentiable there. And then J, the point J is right here, and notice the tangent line has already been drawn for you. Here we have a vertical tangent. So it is continuous. There's no break in the graph. There's no holes. There isn't a corner here. It's still a nice smooth curve. But the tangent line we would draw would be a vertical line. Vertical lines have undefined slope. The slope of the tangent line is undefined. So our function is not differentiable at that location. Okay, so this section is very important, this idea of what the derivative is. Derivative, we encounter the derivative for pretty much the duration of calculus. There are two branches of calculus. We have differential calculus, which refers to derivatives, and we have integral calculus, which essentially will take derivatives and will reverse things around. So we focus on derivatives for quite a bit. There are a lot of applications for the derivative, this idea of finding the slope of the tangent line, then generating that tangent line, those kinds of skills. So what we're going to talk about after this video is other strategies for calculating the derivative. So all of the functions we've looked at so far, evaluating, simplifying the difference quotient is not a super complex operation to do. But depending on how complex your function is to begin with, evaluating and simplifying the difference quotient is not an easy thing to do. So we're going to talk about other strategies we have for evaluating a derivative other than just using the difference quotient. We're going to introduce what we call derivative rules that are going to allow us to calculate these derivatives in a little bit easier, a little bit more of a time-saving manner.